In this video, we're going to provide a quick summary of analysis and design. We've been doing in the previous videos, we have been discussing the design and analysis process, but it's pretty good. It's pretty important to have a conversation here. And as you can see, the way this is drawn, the destinations for the design and analysis are either functional definition or a device schematic. So somebody may give you a device. In our case, in the classroom, would be a schematic where it shows all the connections, and then they'll ask you what is the functionality of this device. And as you move from the device schematic to the functional definition, it's called the analysis process. Typically, when we learn a subject matter or a design or a product category, we usually do the analysis first, learn the analysis process, and then we come back around and do the design process, which is, as you can see the arrows, the design process is the opposite direction. Now, in the class environment, we focus on, when we talk about design, we focus on taking the functional definition, the problem we want to solve, we turn it into a system diagram showing the input, the output, the definition of the zeros. We draw the truth table. We use either K-map or some other technique to minimize and write the output expressions, and then we use the output expression to do the schematics. Of course, we could continue on and basically implement it, which we do in the lab and testing it in real life. You build a product and you have to test it to make sure it does that and all of that. And then the reverse is also true. The analysis is every bit as important as design in the process of engineering. But once we know design, analysis is just reversing the design process. So what we're going to do here, we're going to take the opportunity to do a complete design process. Just to make sure we have that on our belt. And I'm going to take this opportunity also to introduce a concept called modular design. The way we design complex devices is we design simple devices, and as time goes by, we make simple modules and then put these modules together to make a complex design. So for example, let's go ahead and say we have somebody's asking us, in this case, to design an 8-bit adder. Okay, so you think about it and you say, okay, what is an 8-bit adder? Well, the 8-bit adder, the system diagram for the 8-bit adder is going to be basically, and this is a shorthand, instead of me drawing 8 lines to show the one operand and another 8 line to show the other operand, all I do is says, okay, this is 7, or I'm sorry, in this case, we want to do it 8-bit adds. We want to do a 8-bit adder. So what we're going to do is we're going to have 8-bit. So when I put an A in here and 8 in here, it means there is 8 line starting from A0, whether I put it in here or not, starting from A0 to A7. One of the operands, and then the other one is 8-bit, and it's going to be the operand B, the other value we want to add, and it's going to come from 0 to 7. It's 8-bit. And of course, the sum is going to come out of here, and the sum, we know if you add 8-bit to 8-bit, the sum is going to be a 9-bit thing, and there's going to be a sum. So we're going to have, basically, we're going to have a sum 0 through 8. And of course, sum 8 is the most significant, sum 0 is going to be the least significant. But to do this, if I wanted to write the truth table for this, how many rows am I going to have in truth table? I'm going to have 16 input, so my truth table is going to be 2 to the power of 16 rows. That's 256 times 250. It's a huge, long thing we have to come up with. And definitely we do not want to do that. So what we end up doing in these situations is that what we'll do is we'll go ahead and do, instead of doing this, we're going to design a couple of parts and then we're going to pull it together. So what we're going to do is we're going to go ahead and design first. So we're going to break this problem to multiple pieces. We're going to first design something we're going to call a half adder module. Adder module. And then we're going to do a full adder module. Okay, and then we're going to do the 8-bit adder. Okay, so we're going to have 1, 2, 3. So we're going to solve this problem 3 times. Even though it sounds like we're making a life more complicated, actually we're going to make life easier because it's a simpler problem to solve. So let's go see if I can show this. So let's go ahead and for a first step, let's go ahead and do a half adder. So what would a half adder look like? Well, half adder, if I'm let me explain. So when we are adding a number 1, let's say let's write the number we're going to add. We got A0, oops, write this correctly. So the 8 when we say we have an 8-bit adder, we are saying we're going to have an A7, A6, A5, A4, A3, A2, A1, and A0. We are adding B0, B1, B2, B3, B4, B5, B6, and B7. So we're going to add this thing. A0 and B0 add together is going to be S0, that bit adds it, and there may be a carry we're going to call C0. That's going to all add up, and then we're going to have S1 and C1. Okay, if you do this, you will notice that all other bits, go all the way, all these bits except for the very first bit, all the other bits, they got a carry. They got A1, B1, S1, S2, S3, S4, S5, S6, S7, and S8. So if you look at this thing, this operation is different than every other operation that is happening. This is the only operation that is. So this one that doesn't have a carry because it's the first digit, that is referred to as a half adder. The one that has a carry is called a full adder. So now that we hopefully understand why we're doing that, let's go ahead and go and try to design this. Okay. So step one was to do a half adder. Or some abbreviated to half adder. So the system diagram for this is basically I've got an A and I've got a B, just 2 bits coming in, and then I have a sum and I have a carry. Okay, so that's it. So I have a sum and I have a carry coming out of here, and this is a half adder. So that's my, I've got a system diagram to be complete and be able to say I have a full step diagram. I have to design what the values of A, B, S, and C are, and I can simply say that that these are all input and outputs are binary numbers. Okay, so great. So I got system diagram. The truth table is pretty straightforward, and the truth table is going to be input is A and B, output. I'm going to put the carry in here because carry is more significant, right? So that's all possible cases of 0, 0, 0, 1, 1, 0, 1, 1. So when I add 0 and 0, I get 0, 0. When I add 0 and 1, I get 0, 1. I add 1 and 0s, I get 0, 1. 1 and 1, I get 2. Well, we don't really need to. Next thing we need to do is go ahead and do a functional expression for the outputs. In this case, we would have a function. The output is C, the carry. The carry is simply A and B, done. And then S is simply going to be that it is exclusive OR. You can do other things, but exclusive OR is a nice one to put in here. It's just one gate and I'm done. But here we have it. So what we could do, we could actually do a schematic, a quick schematic for this thing. And basically the schematic, it's pretty obvious what the schematic, we got an A and a B coming in. We're going to AND it together. Then we got to take it out, exclusive OR it together. And then what we've got, this is going to be the sum, and this is going to be the carry. Okay, so what we do a lot of time, instead of having to redraw this every time, now that we've shown people how to do it, we don't have to give them the detail anymore. So we'll make a module which looks kind of exactly like a system diagram. We say this is a half adder, so they know what it does. And then we're going to say you put A in here, A in here, you put B in here. What you're going to get out is a carry, and you're going to get out sum. So we build our half adder. So if we go back and take a look at this, now we are able to do this operation. Now the next thing we got to do the second part, which is the full adder, so we can be doing the operations there. And if you remember that operation's got a carry coming in. So we're going to try to generalize this. Instead of having this just a carry and a sum bit, we're going to say, okay, if you've got, so we're going to 2, and the second problem we're going to solve to figure out how we do full adders. Okay, I should use a capital letter, and FA. All right, so a full adder would be, the system diagram for a full adder would be full adder, which eventually we're going to call this a module. And the full adder will have 3 inputs coming in. We've got the 2 operand, A and B, and then we've got a C in. And then what we're going to come out of here, we're going to have a sum, which is the sum of all 3 numbers, and any carryover, we're going to call it carry out. Okay, so the names hopefully will make sense when we get to the third stage and build a larger adder using this. So that's great. And again, we can copy this comment, which all, so make sure the system diagram is complete. All inputs, outputs are binary numbers. All right, so our truth table would be a little more complicated than that one. So if you look at this thing, is going to be A, B, carry in, and then we've got carry out, and then we've got the sum bit. And then let's go ahead and write this truth table. We've got so if I do 0 plus 0 plus 0 added to 0 added to 0 will be a 0, which is 0, 0. 0, 0, 1 will be 1. 0, 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 0, 0 is 1. 1 plus 0 plus 1 is 2. 2. And finally, the biggest number is 1 plus 1 plus 1, which is 3. Okay, so I've done this. Now my job is trying to see if I can minimize this thing. And the easiest way to do that, of course, based on what we've learned, is to do a Carnot map for for C, 0, and S. So let's go ahead and do that and see if we can come up with something nice and clean. So we've got A, B here, we've got CI here. So all right. Okay, so this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Then we're going to go down here. This is 0, and this is C out, Carnot map for C out, 0, 0, 0, 1, 0, 1, 1, 1. Okay, so hopefully I got that right. If I did that right, then you look at this thing and say, okay, what is the best way I can handle this? Well, we can write this as CF out. There's one prime implicant, another prime implicant, and another prime implicant, and all of them are required. So what we're going to have is, for this prime implicant, we're going to have A and B. Oops, this is an A, poorly formed. And then this one is going to be BCI, BCI. And then the last one is going to be ACI. Okay. And then, of course, we can follow the same process and do one for the other input we have in here, which is sum. So now we're going to do the sum one. So again, we draw a K-map. And we're going to fill it this time with the sum. Sum is 0, 1, 1, 0, 1, 0, and 0, 1. This one, if you remember, this is a pattern that really calls out for a exclusive OR situation where as long as you have odd numbers of 1, it's 1 if you look at this thing. And this pattern of every other being 1 usually should warn you that, hey, this is exclusive OR, and the easiest way to do this is probably do an exclusive OR. Okay. All right, so we've done it. Then the next thing we need to do is go ahead and do the schematic for this one, just to simplify the schematic for what we're doing here. It's going to be basically you have a, let's draw this thing. So you got a box, and this is called a full adder. We usually put the name in the middle. We'll put the input names in the inside, C in, and what comes out of here is S and C out. So there we have it. Oops, this is actually the module. So if I want to do the schematic, this is the module. So when we want to use it, we just drop this in. We know inside this is pretty simple. If you wanted to do the schematics A and B, ORed with B and CI, ORed with A and CI, that gives us a C0. And then we do a 3 exclusive OR, and that gives us the S. Okay. Now I've got this. Now the question is, the original question for this problem was, can you do an 8-bit? We can actually do a 32-bit, 64-bit, 128-bit, whatever you want to do using this scheme. So let's go ahead and take a look at it. Let's go back to the beginning of this one, and So we want to do an 8-bit adder. We have this module, which is a half adder, where it doesn't understand a carry, that can be used for the first one, and then this full adder can be used for the rest of them. So let's go back here, give ourselves plenty of white space. Okay, so this is gonna be our 8-bit adder. So what we're gonna have basically A0 and B0, the least significant bits. They're gonna come in, and we're gonna put them in our half adder. We're going to connect this to the A of the half adder, B of the half adder, and then S comes out of here, and then the carry out comes, or the, well, I think we call it C, and this C comes out of here. So this is going to come out here. This becomes the least significant bit of our sum. And then now we're going to have to use our full adder, and then we're going to have a full adder here, one of our modules. We build one and put it in. And now we're going to have, we have a C in, we have the extra one, we have our B, and we have our A. So what we're going to do is, in this case, what we're going to do is we're going to take the carry from here, and we're going to put it here. And then we're going to put our B1, A1 here, the next value. And then that's going to give us the sum 1 from the sum side, and then the carry out from here will come out, and then we're gonna have basically carry in, B, A, full adder, sum, carry out. So we got A2 in here, B2 in here, and then boom, goes here. So now you can see how we can continue this to however many bits you would like to have. So let's say we have n can be any arbitrary number you want to pick, and bn comes in here. So you're going to have the carry is basically going to be the previous carry, Cn minus 1. This is going to come up, and it's going to go in here for the C in, B, and A. And what you're going to have, this carry out, and the sum is going to come out here. So the sum is going to be Sn, and this is going to be Sn plus 1. When we sum two numbers with n bits, we're going to be, in this particular case, n is equal to 8, but you could make n equal to anything you like. And here now we have as big a adder as you want. So my question to you, and for you to consider and think about, since we are already a long video, we're not going to do it here. How would you do a n-bit subtractor? And how would you do, well, let's do the subtractor, then we can have a conversation about multipliers and divided at later videos.